With unsupervised learning, so with supervised learning, what we are ultimately doing is you're taking a bunch of inputs and you're relating that to an output, and you're trying to determine what function will actually do that. With unsupervised learning is you don't really know what the you have a set of features, but you have absolutely no idea how to classify them. So it's sort of self-organizing in some way. So it's several, I mean, there are a lot of things, as we talked about. You have clustering and detection of patterns is typically an unsupervised learning problem. Compression, so basically this would be, an example could be autoencoders where you can basically only send partial information and have the AI reconstructed on the other side. Dimensionality reduction is what we're going to talk about in just a moment, and that's where we if you have a ton of different features, it's a way to reduce those features into a much smaller set, which is kind of relating to that. It's also data visualization, which allows you to see patterns. So the challenge is that with unsupervised learning, it's not as straightforward as supervised learning in the sense that it's a little bit more subjective. And there's really no like what you're trying to get out of it's not as simple as like supervised where you're relating an input to an output. Supervised learning is very straightforward, whereas with unsupervised learning it's not always clear what it is that you're trying to get. And one of the key factors of unsupervised learning is that the human factor is not needed. So you don't have to go in and label data. So one of the, so this is not a neural network approach, although there are approaches to doing this with neural networks, but this is something called principal component analysis. And so principal component analysis is where you're trying to reduce a very high dimensional space to something which is much smaller. And why would you want to do that? Well, visualization is one of the key things. Another thing could be that you're trying to reduce the number of features. So feature reduction, dimensionality reduction, visualization, these are all factors that help, for example, prevent you from building a model that's overly complex. So it helps simplify that. So for example, if you reduce the number of features, like for visualizing, it's one thing. And secondly, if you later on want to use this as part of a classification problem, then you can also use the reduced feature set or reduced feature set for building up your model. So it could actually give you, this is one way potentially to help solve solve overfitting issues and so on. Right. So one of the things that it does is there is loss of information anytime you go from a high dimensional space to a lower dimensional space. There will be some information loss as part of the process. It's not like no information loss type of thing. What you're trying to do is find out the most significant vector. So if you're trying to get a huge number of dimensions, what you're trying to do is figure out in a lower dimensional vector what is the vector that is most representative of the higher dimensional space, which is and obviously what you're trying to do is compress a whole bunch of dimensions into a single vector, which is by nature you're losing information. I mean, that's just how it works. But so the way that PCA works is it tries to reduce the amount of information loss in the process of actually calculating that principal vector. So that's what we're trying to do here. So there's more math. So basically here, what we have is, suppose you have a bunch of observation of sort of n features. So what that means is you have x0, x1. So an observation, what does that mean? You have, when I look at a system, I have a bunch of points, and I've m of those points, and this is part of an n-dimensional space, Rn, so which means that each of those have n features. So if I were to write it out, I would have, so you remember like a feature set is like a bug might have a name of the person, the severity, priority. Those are all features. So if I talk about n features, what that means is you have a set of vectors. So let's say you have, so these are your observations, x0 to xn minus 1, right? So those are observations. So those are, for example, these are all of your bugs, for example. You're using, let's say, n is equal to 1,000. So then you have n minus 1. So it's like you have 1,000 bugs as part of your training set. And each of these bugs would have features associated with them. So you have, let's say, x00, x01, all the way to actually it's m minus 1 because to stay consistent. And then it's x0, n minus 1. So what that means is that this x0 has n different features. So this is m. So altogether, you have, if you calculate it, you have n times m possible values in the system. So then this goes down here, and you have x m minus 1, 0, all the way up to x m minus 1 and n minus 1. So this is basically m minus 1 observations, where each one of these observations has n minus 1 possible features, right?
Yep.
Okay. So the next thing we want to do is we're now going to try and calculate the first principal component. So the principal component in this case is the most representative vector in a different dimension. So the way to think about it is, suppose I have a three-dimensional space. So suppose I want to now reduce it into a two-dimensional space. What I'm then doing is trying to figure out two vectors. One, and they represent, so you have a bunch of points, which are your observations. And so what I want to do is calculate the one vector that's most representative of all of these points. And then after, suppose I want to reduce it to two-dimensional space, and once I've calculated that, then the next thing I want to do is calculate the second principal component, which is orthogonal to the first, and you don't know like exactly what it is. But that second principal vector will be the second vector that will give you that's the most significant based on the observations that you've made. So, and you keep doing that. So this is the three-dimensional space being reduced to 2 dimensions. But notice that these vectors are still three-dimensional vectors. So you're not changing the dimensionality of the vectors. But when you reduce the number of, when you're trying to reduce the dimensions, what you're trying to do is figure, like when you reduce it down to 2 dimensions, what you're saying is that you're taking a three-dimensional space and you're reducing it to 2 dimensions because now you have 2 vectors. So you're essentially generating a plane in this space. So these two will form some sort of a plane, which is your reduced size of the, is your reduced dimension. So in effect, that what you're doing is you're getting all of your three-dimensional points and you're mapping them onto a 2-dimensional plane, which represents the most significant representation of that 3-dimensional space. Does that make sense to everyone?
And that's automatically mapped.
Yes. Yeah. So the way to do this, and I won't go into a ton of detail because this involves like matrix multiplications and figuring out transposes and things like that. But what you do is, the first thing is you define something called a loading. And so this is kind of like what these are alphas are. And the set of loadings and the vector is called a loading vector. And what you're doing is the first thing you do is you normalize it. So the loading vectors are basically, this is your first principal vector. And what you're trying to do is you want to calculate what that loading value is. So in other words, what is the loading vector that will actually get you the principal component? What that is that this vector here in three-dimensional space, this vector has 3 coordinates still, right? So it'll have like A, B, and C. But this is a vector in three-dimensional space, which is your principal thing, but it still has three coordinates. And this will also have 3 coordinates. But the two together generate a two-dimensional plane. What you want to do then is you want to calculate what are the values of A, so the vectors. So what are the values of A that this is kind of called a linear combination. So you want to figure out what is the linear combination that will actually get you that initial vector. So the only condition you have is that the loading vector that you're generating is a normalized vector, which means that the sum of if you look at the Pythagorean theorem, it means that the distance from the origin is 1. So that's the only restriction you're placing on that. So the loading vector is basically, so these are all the loading vectors correspond, and you have the i's correspond to, so for example, you could have I0, 1, I0, 2, I0, 3, and so on. And so this is basically called a loading vector. And this is basically just the features corresponding to that, observation. Any questions about that? Right?
Quick example.
Sorry?
Any example in the real life?
Well, an example would be, suppose I have, let's say let's say you've got age, weight, height as describing somebody, right? So suppose you want to now say, instead of age, weight, and height, you want to represent weight and height as a single value. And so I don't know what that represents exactly, but the advantage of that becomes easier to graph. So then what you do is you combine weight. So right now, if I were to write age, weight, and graph, the way you typically see it in the doctor's office is you have one thing representing weight and another thing representing height, and then you have some sort of bizarre curve there. And that you put, now suppose you want to put that all in one graph. And at that point, what you do is you can combine the weights and heights into a single dimension, and you can have a single graph that represents everything. But so that becomes easier to visualize, and that's actually used. So you're combining a bunch of factors which might be related in some, or that you just kind of want to condense into one observation, because it's hard to visualize 10 dimensions because you've got all these different features, and you want to basically have it visualized as a simple two-dimensional thing that you can see. Does that make sense? Another example could be if you want to build a model around DNA, right? You've got coordinates, positions, to define DNA as a set of values, it's very tough. You've got a lot of dimensions that correspond to that. But if you want to kind of visualize it in a way that you can use to manipulate it and observe it, you reduce all these dimensions maybe into 2 or 3 dimensions, which allows you to visualize DNA in a simpler way. So there are different ways, for example, to collapse data, to visualize, to work with, to maybe also to identify patterns. If you want to see clustering, because sometimes how do you see clustering in 10 dimensions? The way to do that is reduce the dimensions to a much smaller space. So for example, if we look at age, weight, and height, if you want to look at clustering in 3 dimensions, because that's 3 dimensions, that's a lot harder. But if you can condense weight and height into 1 dimension, then you've got age and this weight-height combination, and that allows you to visualize clusters of ages and weight heights and so on. Does that make sense? So for example, if you want to look at growth spurts, that could be an example where that would come out. That you see that, okay, age, weight, height combination was in one cluster, and then suddenly jumps into another cluster, and that's because people have these little growth spurts along the way, in which kind of then you can see clusters forming.
Could you get, like obesity, normal weight range?
Yeah.
The low weight range.
Yeah, weight, height, exactly. That would be another thing. Yeah. For example, another thing could be age, weight, height, health status,
Right.
or something like that. in which case then you may want to see that combines all of these elements together, easier to visualize, and you see clusters forming. So that's how you'd use it. So another way principal component analysis can be done, can be used, is suppose you have 20 different features, but you don't know which feature is the most important. Like each of those features contribute to the whole. So what you may want to do is reduce, so for training purposes, if you want to build a training set, you say I've got 20 features, but what I'd like to do is I don't know which of these, so I've got like one and then maybe 3 that you think are significant, but you don't know what the overall significance of the others are. So you may, for example, use principal component analysis to reduce those into a single dimension or a single feature, which you then use for training, which then encompasses all of these others together. This can also be used for explainable AI. So for example, you can use principal component analysis to play around with how you combine things together, and then you figure out which of these features has the biggest impact on the final value. So you can use that in many different ways. Make sense? So, so AI Studio will soon support this out of the box. So you can actually do that as part, but it's a point release away. So then, so how do you know this is the most important component? So what you want to do is ultimately you want to find the weight, you want to figure out what value of this vector is going to maximize the distance between each of these components and that vector. Why is it that you're trying to maximize the variance? Well, if you try and so when you maximize the variance, it means that you're finding the one vector that is taking into consideration the most variance in the data. So if you have something in which takes the least variance in the data, that means it's not significant. It means that you're not really considering a lot of factors. So what you want to do is whatever variance you see in your original data, you want to figure out a vector that is able to count for that variability, which means you want to maximize the variance from that. Does that make sense? And so this is essentially what this does. I'm not going to go through the rest because that requires a little bit of linear algebra. But so what this basically will do is, yeah, there's just a way to do it. You calculate the covariance matrix, and then you do singular value decomposition, and you get the output of that. But the principle is what I just talked about.
So as far as trying to understand that, maximizing the variance,
Mm-hmm.
if you're going from 3D space to 2D space,
Mm-hmm.
the best principal vector would be the one where on that plane you created, you would actually see the most variance of points on that plane?
Yeah, it would be the one where you see from the original observations, the original points, you see the highest variance between the vector that you have and the points that you've observed, because that vector means that you're taking into account that vector represents the most fluctuation in your original data, which means that it's most sensitive to any changes in the original data. Right? So you want to figure out the vector where if you change the original data, that results in a very significant change in the vector. So take something that is, yeah. So to figure out that principal vector, that's what you do. So you want to maximize the variance between the points that you have and the actual principal component. So I'm not going to go into that because I mean I don't know how many people like have a linear algebra can do. Like, yeah, okay, so it won't make any sense. So